Thank you for coming back. This is a tutorial, but it's only 45 minutes long because we all need to go and find out about the APNIC member survey. We actually all do need to go find out about that. That's really important. So this is kind of SDN, Openflow, seeing it a bit in action, how you might want to go about installing it just to have a play. The first bit of this talk is a little bit about demystification of what I mean by SDN. At the moment, you know, SDN's a bit of the buzzword of the day. Everyone's got one, but no two people mean the same thing about it. So I'm going to go through a little bit about what I mean about it, and then for the last bit, I've actually got a bit of a demo of showing you the bits hanging together and explaining a bit how you might want to get started and play with some of this yourself. So who am I? I'm a man of many hats. I'm a trainer and network engineer for the Network Startup Resource Centre. I'm an SDN research associate at the University of Wellington. I'm a technical policy advisor for Internet NZ. Yeah, I do a lot of stuff. Some of it relates to SDN. If you haven't played with this much before, you've probably got some questions, right? They might go along the lines of, what is SDN? What's wrong with the network I have now? What can an SDN do? So I'm going to try and answer some of those quickly, and then, as I say, go into a bit of a demo. So SDN primarily is the stupidest name ever invented. Okay? It doesn't actually explain what the concept is. It kind of does at a really high level, but not very well. And if you try and explain it a little bit more detailed, you end up with far too much words and not enough actual getting the message across. So what it is, at the easiest way to explain this, is it's a way of splitting everything about your network in half. It's a way of decoupling the system that makes decisions about where the traffic is sent from the actual parts of your network that deals with actually getting it there. So all of the hardware that actually forwards the packets, takes it from that port to that port, that's down at the data plane, all right? But all of the data plane stuff doesn't really have any intelligence about how or why the packets are routed that way. All of that intelligence is up in the control plane, and a defining feature of SDN is splitting those in two, okay? A control plane and a data plane. And that's something that we're going to come back to time and time again throughout this. So you've probably had software-defined networking for years and years and years, right? Anyone own a Juniper M-series router? Yeah, a couple. You've got SDN, congratulations. All right. Yeah, so Juniper M-series does that split, right? You've got the routing engine in the back running all the protocols, running, it was BSD back when I was there, you know, running BGP, running OSPF, running all of the control level stuff is in the routing engine, and all of the actual forwarding the packets around is done on the packet forwarding engine, and they're split. They're just in the same chassis. Well, I say that you've got an SDN, but the thing that I really want to get across is it's a little bit different than what we're talking about now, because you can't control the software, okay? You install Junos, and that software controls both the hardware forwarding part as well as the control layer part. You don't really get any say. You can configure them, but you can't control it. So let's go back in time, right? Let's turn the clock back and see a little bit more about what I mean. Anyone remember this? No? I got grey hair, so I remember that. All right. So remember back in the day when this was sort of your operating system, and if you weren't a Windows guy, then remember back to Solaris or Irix or HPUX or any of those runs, right? If the features you wanted were supplied by the operating system, you were in luck and you were having a good day. If the features you wanted were not supplied by the operating system, there were very limited opportunities for how you were going to expand to be able to include those features. Now, I don't mean applications, right? I don't mean installing apps. I mean actual operating system features. Let's think about v6. Very limited ways to shoehorn IPv6 into an operating system if it's a closed-source operating system. All right. Well, we moved on a bit. We got some choice. Part of that choice came from open source operating system environment. So with the open source operating system, the control over the development and deployment of the features was placed back in the hands of the users. All right? The speed of deployment, the direction of deployment, and all the innovation around those features was given back to the users rather than in the hands of the vendors. If you needed a feature, even if you were the only person on the planet who thought that that was a good idea, then you had a way of making that feature happen. You could write it yourself, you could hire someone to write it, you could download it from the other guy on the planet who thought that this was a good idea. You had options, okay? Now, a lot of people have made a lot of good things out of the ability to do permissionless innovation, okay? Would we have a Facebook? I see someone squinting. The small text is just the kind of reference, but you can download the slides later. Facebook, Google, Android, etc. make heavy use of this open source environment because they can control the pace of innovation. They don't need to ask permission to innovate these new features. So now, fast forward in time again, right? Think about the current networking equipment that you have. Think about the current routers you buy, the current switches you buy, firewalls, load balancers. Do they look more like the closed-sourced operating system past, or the current operating system world where you can kind of choose how that innovation happens? Past, present. Okay, well let me run through this a bit. So here's how having a good idea happens in networking today. You have a really good idea. Maybe you're configuring your network and you're like, oh, hey, I've got this really good idea for a feature that would really help me out. Well, what you do is you go to your network vendor, the person that you buy your stuff from, and you pitch your idea. Say, man, I've got this really good idea. It'd be great if your system did this. They will turn around and ask how many new units you're going to buy if they implement that feature. Whatever number that is, it will almost undoubtedly not be enough. There are some customers on the planet for whom that number is enough, but it depends on where they are in their refresh cycle, right? Almost always, I come from New Zealand. Everyone in my country, that number's not enough. Because you're absolutely right, because it's small. Yep, and we're a feature taker rather than a feature leader on this, right? So the upshot is nothing happens to your, nothing happens regarding your good idea. It dies. Here's another example. Hi, Mr. Load Balancing Vendor. I'm a CCTLD in a small country. We face unique challenges regarding managing bandwidth and protecting against DDoS attacks. We own 2 of your load balancing units, and we're wondering if you might be able to assist us with these unique challenges. At which stage there's a click and a burp. Okay? I'm being a little bit harsh here, but I think people would agree I'm not way out, right? The opposite's true as well. How many times have you kind of seen this from your networking vendor? We're pleased to announce that after months of development, the new version of our networking software will support some feature you don't need. The price of the next software upgrade will be double to recoup this development cost for the feature you don't need. Okay? This happened a lot around back in the days when MPLS started to be the one true way. For everyone who didn't want to run MPLS in their network, they just ended up paying for everyone else who did. So what if we lived in a world where you could start an open source project where people could develop the features you actually needed for the platform. You didn't have to pay for features that you weren't going to use. And even more so, you didn't need to worry about the bugs in the code that you weren't going to use and weren't going to deploy. You know how many millions of lines of code there are in the latest kind of networking equipment? And you don't use half those features. So don't have them on the box. So this kind of mindset works today for operating systems, right? It works really well. If you need a new extension to Apache, Bind, MySQL, etc., you can have someone develop it for you. What if you could do the same thing for all of the features in your switches, routers, load balancers, firewalls, etc.? That would be kind of cool. So my suggestion is that software-defined networking allows you to do just that. It allows you to take back control of the software that controls your network, and it allows you to drive the speed and direction of innovation in the direction that you want it to be, rather than the direction that someone else wants it to be. Cool. That's the spiel. How? So as I was saying when we started, it's all about separating that control plane from the data plane. There needs to be an open interface between those so that we can talk between them, and I'll go into that a little bit more later on. And now I can have all of my network control and management features in software. If I separate that and bring all the smart stuff, all of the algorithms, all of the computation up into that control plane, which is operating on an open framework, then I can start to develop that software. So here's an example of what networking hardware looks like today. So on this side here, these are individual routers, switches, firewalls, whatever. It's pretty much the same. And they all have this specialized packet forwarding hardware, right? They've all got the little ASICs and chipsets on them that get, the packet from that port to this port. But they've also got this operating system in the middle, and then they've got all these features that sit on top. These might be the same as these, they might be different to these, etc., but each one has that set. And it means for you to get knowledge about your network, around your network, you have to have all these protocols that exchange the topology, exchange the traffic stats, all that around here, because each of these is running one little part of the control of your network. You have decentralized control. What we want to do is move to a model which looks far more like that, where we've still got the specialized packet forwarding hardware down the bottom, but we've taken all of the, effectively the network operating system up to one single instance, and then the features are deployed on top. Here's a slightly different here's a slightly different diagram. Andy Linton, who some of you know, likes this one, so I've started calling it the Linton 3-layer model just to see if that takes off. So down here, again, we've got the infrastructure layer. This is really my fabric, all right? This is all of my switches plugged together so that I've got ports all over the place, and the only job that this layer here does is pass packets from A to B. This port to this port, this port to this port. Just passes packets really fast, does nothing smart, has no control, makes no decisions, nothing. Up here is my control layer. This is where all of the decisions about where traffic goes is made. So the decisions are made here, and the actions are done here. Decisions, actions. And the protocol which we run in the middle to get my decisions down to be actions is called Openflow. And some of you might have heard about Openflow, and some of you might have heard it used almost the same as SDN. I've got an SDN network, I've got an Openflow network. People use them as the same thing, but they're not. SDN is kind of the concept that I've been telling you about up until now, right? This whole splitting the thing and innovating and that sort of stuff. Openflow is just a protocol between a control plane and a data plane. That's it. It's a protocol, it's got a spec, it runs on TCP port 6633 most of the time, blah, blah, blah. It's just a protocol. So don't let people confuse you with, Openflow. It's just a protocol. So that seems like, and then your business applications are kind of on top there. So that seems a very simplistic way of looking at our network. Much more simple than maybe the 7 layers or more that we're used to dealing with today. But here's a couple of quotes from Michael Poplitsky. If you know what you're doing, 3 layers is enough. If you don't know what you're doing, 17 layers won't help you. Okay? So if you know what you're doing and you're careful about this, and remember you're only dealing with the features and software that you actually want to deploy, then 3 layers is fine. The flip side to that is be careful of panacea peddlers. Be careful of people who are going to tell you that SDN is the only solution to things, right? Including me. Be careful of me. Everyone needs to think about this for themselves, right? Just because you wind up naked doesn't make you an emperor. All right? Just because I'm telling you about SDN doesn't mean that it's all great. Validate this stuff. Validate this thinking yourself. All right. So how are we going to do this? How does this Openflow protocol work? How are we going to take the decisions at the top level and turn them into actions in our network? Well, hands up who's done any sort of programming. It doesn't matter what language at all, right? Basic, Pascal, right? So people are familiar with conditionals, right? If this, then this, right? If a certain set of match conditions, then perform these actions, all right? That's essentially all we've got going on here. I take all of the things I want to do on my network, and my Openflow controller turns those into a set of if-then statements. And I'm going to call those flow rules. All right? There's one over there, but I've got a couple more slides where it shows them better. I put those if-then statements down into my network, and I use them to match packets very, very quickly. So that's essentially all the magic there is. We've got some time left over. No, I'm kidding. But that is about as simple as it is. There's some magic there in how you build those if-then statements, but that's essentially all we're doing. So here's what a flow rule looks like. It's got a rule spec, it's got an action or a set of actions associated with it, and it's also got some stats, okay? So the rule here, I can match on any number of a multitude of things. Who was in Jeff Houston's talk this morning? Hearing him talk about what's special about 512. Yeah? You heard him talk about TCAM and how TCAM memory can match on the contents and give you a very, very quick response. That's all that's happening here. Okay? So I'm doing a match on any number of these, and based on these matches, the if conditions, I'm then doing a set of actions. And we're going to see a little bit more in the next slide. So let's think about that a little bit more. Now, I'm going to ask you guys some questions, and I want you to ignore the first column here, which contains all of the answers. Okay? So that first row up the top, if this is the match condition to my flow rule, and I don't care about the input port that the packet came in on, I don't care about the source MAC, but the destination MAC must be 12.2e, and the rest of it I don't care about. If I'm doing packet flow based on a destination MAC lookup, what am I kind of doing? What function that we do in networks today all the time is that kind of like a destination MAC lookup and then do an action? It's like layer 2 switching, yeah. There's the answer, right? So that's the equivalent to just doing layer 2 switching. I'd write a flow rule. I'd say, okay, there we go, match that destination MAC address and then do something with it. Here's another one here. Don't care about any of this. But if the destination IP address is this, or 1.2.3/24, I can do a prefix here, then do something else. All right? So if I'm doing destination IP matching, that kind of looks like IP routing. Yeah, cool. Chocolate fish. There you go. All right. Similarly here, if I'm looking at destination ports, squint your eyes a little bit, and that looks like firewalling. This is normally the time in the talk when someone yells the word stateful at me, and I have to capitulate. But go with me here, just for a minute. So these are the sort of flow rules that I would write to achieve kind of the things that we know how to do today. Well, that's not really exciting, except now I get to decide how those happen. What's more exciting is I can do arbitrary amounts of matching in here and accomplish tasks I can't do today. Now, I can do flow switching. I can say I want to specify every single thing about the packet and then actions on it. Okay? Now this blows across your layer 7 model, right? I get some stuff here at layer 1, input ports, stuff here at layer 2, layer 3, layer 4, and I'm just going to match all of it and assign an action in one step. Okay? Or I'm going to do some stuff here at layer 2.5 and layer 4, and that's what I'm interested in. And I'm going to develop a whole set of software which develops these rules and pushes them into my data plane that look like that for some weird reason. Here's another one, incoming port plus Ethernet source address plus an ether type and something about the IP. Yep. Good question, and people should feel free to throw their hand up. Yes, this is just what I can fit on the slide. And certainly the Openflow spec, as it moves through version 1.0, 1.1, and we're up to 1.4 now, they add different matches. So prior to 1.2, there was no V6. But 1.2 added the entire V6 spec here. We had MPLS label support added. There's VLAN tag support, obviously. You can match on diff-serve code point. So it's not complete yet. I wouldn't say that this was going to do deep packet inspection anytime soon, but it could. That's going to be a limitation on the TCAM before it's a limitation on the protocol. But certainly in terms of headers between kind of layer 1 at a squint, but layer 2 to 4, we're getting pretty good about being able to arbitrarily match those sorts of things. V6 extension headers are a little bit trickier, but yeah, we're getting there slowly. Yep. Oh, yeah, true. Yep.
One of the things that we do really well now, because we segregate the layers, is that we've got predictability in terms of we know exactly how much we're going to decap and encap at each device. So we can design hardware to deal with that. All the vendors can. Does SDN have any thought around how you deal with that? Or
Yes and no. So remember conceptually there's that split, right? So the only layers that we're actually really still treating as the rule is the fact that the control layer is separate to the data layer, is separate to the data path. So at the control plane layer, how I packetize and serialize the packets and match them in buffers and do this checking isn't my problem. It's also not really a problem for the Openflow spec in between. It's an implementation detail on the hardware. Waves hands, smoke appears, right.
So we want, as Cisco and Juniper
I don't know, and if I did know, I probably wouldn't say on a streaming video link what they were doing about it. But there are vendors which are doing more or less in this space. So I certainly know that there's some vendors where you can match layer 2 like fields or layer 3 like fields, but not both. All right? And there's some vendors where if you want to do a flow switch like this, then you can do 1,000 of them per chassis. But if you want to do ones like this, you can do 12,000 of them per chassis. So there are certainly leaders and laggards in that sort of stuff in this field. Cool. Hopefully that means I can still get jobs. So what are some examples about where we might want to use these sort of concepts? Layer 2-ish stuff, and I mean, once you start thinking about this, I really go away from the layers, and I'm starting to go away from the concept of switches and routers. It's really, really tempting to start calling these things switches, but they're kind of not. They're just, a friend and I came up with the term, just a bunch of ports, a JPod, or a JBOP. They are just a bunch of ports. They can be a router today, they can be a switch tomorrow. Half of them can be a switch, the other half can be a router. So, you kind of get away from those traditional concepts as much as possible. So where we're seeing a lot of layer 2 stuff in this is really around the network virtualization, data center, multi-tenant stuff, where what you want to do is you want to take the physical network which you've spent so much money on within your data center and replicate it 3 times. If you had to build one of these for each client, then you could only have one client, or it would cost a whole lot. If you can actually do meaningful overlays and replicate this out within your data center, that's where the money is to be made. And certainly when you can start doing things like taking the network infrastructure around your VM farm, putting a centralized network operating system layer and then different application loads on top, and implementing those as flow rules down on your top of rack switching, then we're certainly starting to see some really mature stuff in that space. Similarly, layer 3 and routers. There's a system called RouteFlow, which takes an Openflow fabric here and lays a virtual router on top. So basically, the router is just up here running in a VM. And it could be Zorba, it could be Quagga, it could be Bird, it could be anything. And it's just running in a VM, and the controller just maps a couple of ports into it. So this port here in this city, and this port here in this city, just get mapped into this VM here. Now, that's not so special, right? That just means that all of the traffic that wants to go from here to here has to trombone through this VM. That seems really stupid. But what if I could have this router see the BGP traffic out of these ports, but the actual transit data was fast switched across the fabric using those flow rules. So I get BGP to happen up here in the VM, and once this guy learns prefixes, the controller turns those prefixes into flow rules on my fabric, and then the actual data is fast switched and never leaves the fabric. Well, that's a cool idea, and we're actually doing it on the Wellington Internet Exchange. So between the Wellington Internet Exchange over here in New Zealand and RIANZ, our research and education network, we've got a bit of an Openflow fabric here. We've got Quagga living up in a VM here, pushing down basically a fib. It learns all the BGP stuff from RIANZ, it learns its BGP stuff from Wix, and it pushes that down as a fib in the form of Openflow rules down to here, and these guys just do hardware-based forwarding. Now, what that means is we can arbitrarily add new features at the speed of Linux, rather than having to wait for the speed of insert vendor X. And the example here was in about 24 hours, we added RPKI. So we had a rower cache, and we just used the rpki.net framework. Just go and download it. It's Debian packages. It's great. So we downloaded that framework, ran that all up on this guy. He was looking at the global RPKI database, and that was affecting the hardware flows down here. So if you told me about a BGP route that had an invalid rower, I didn't put that flow rule into the flow table. So I have hardware implementation of RPKI that we did in basically 24 hours. And this has been running for about 3 years, and just when I left, it was up to 108,000 routes. You know, is it a full table? No, but we're also running it on whatever hardware that we can big, borrow, and steal, right? So you can add new features without waiting for the vendor to be able to support them. You get to decide what's important. You get to decide how you roll it out. You know, load balancers need to take into account a lot of information that has nothing to do with the network. That's kind of what they do, is they balance your network traffic based on things which are nothing to do with your network. You know, how busy the servers are, how many clients are coming from over there these days. Seems like a perfect SDN approach, right? You can tell the control plane about that, and the actual load balancing can happen down on the data plane. There's a couple more examples here. There's a good one about firewalls. What if I could take all of this mess, compile the flow rules down, magic hands, turn it into something which looks like this. Still got the fabric, but I'm actually doing all the firewalling based on the flow rules here, rather than segmenting. That's pretty brave. I don't know that I want to do that in my network today, but I think we'll get there. A lot of work happening in New Zealand on SDN at the moment. We're doing some work at the university, the exchange, the New Zealand Internet Exchange, rather than just the Wellington one, is looking to redeploy on an Openflow powered SDN basis so that they can guarantee what the forwarding path looks like. If you don't give me a BGP route, I won't let you move that traffic. So, you know, today, internet exchanges kind of work by the honor system. You give me some BGP routes, that's cool, but if you just want to put random packets on the exchange with a MAC address of a destination over there, then I'm kind of going to carry them. But what if you can say, unless that peer advertises that route, I'm not going to let you send packets to them. And that's what they're looking at doing on that exchange. We also did you know, a hands-on half-day install at NZNOG. It's basically going to be what I'm going through here, but we actually had some hairy geeks in a room and went through and did some installation on the hardware. So I've almost stopped speaking about this, and I think I've got time for the prezzo. What are the takeaways? The important thing to remember is whenever anyone's talking about SDN, they had better be talking about separation of control and data plane. If they're not, they're just trying to sell you something. It allows us to have a holistic view of the network that wasn't available before, because that control plane sits across the whole network now. It can see all of it. Yeah, they are takeaway logos in the background. You know, that we just didn't have before. It allows you to control the direction and speed of innovation, as I said. It's an active area of development. Everyone's kind of having a go at this at the moment. Some people better than others. I know some people whose view of SDN is TCL scripts controlling SNMP queries, controlling the data plane. Sorta. I reckon if that's all their SDN story is, I think they're getting it kind of wrong. But you know, it's a big spectrum. Any questions about that before I crack into the demo? No? Clear as mud? All good? Yep. All right. So what we've got going on at the moment is I'm teaching a fourth year course in network engineering at the university, and what we're making the students do is actually deploy a control layer and deploy a data plane, look at the interaction between them, and write some features on the control plane to deploy new features out into their network that weren't there before. Okay? And I'm making them do that in 3 weeks. They don't like me. So here's kind of the topology, and because we're all old school, you'll appreciate the ASCII art. So we've got a controller up the top there, we've got an Openflow switch in the middle, and we've got 3 hosts down the bottom. Now, because we don't all have an Openflow switch lying around, we have to use a simulator. Okay? So what we're going to do is we're going to use an actual controller, and the switch and the hosts we're going to simulate in a system called Mininet. And that's just a simulation environment where I can tell it how many switches I want, and I can tell it how many hosts I want, and it will communicate with the Openflow controller. Right. And of course, live demos never go wrong, so I thank you in advance for your patience. Now, what I'm hoping to do is make this VM available to you guys. It is 1.3 gigs, so I wasn't going to put it up on the network and say have at it, but I will put it somewhere, and all the slideware and the worksheet as well. So yeah, we're going to SSH in, open 2 windows, become root. We're going to do that. So here are my 2 windows here, right? Live demos. Go. Almost. Cool. Top window's my control plane, bottom window's my data plane. So I find it easier just to do everything as root, especially when I'm playing on lab boxes on a VM. I know that's terrible, I know I'm evil, I know, yeah, I don't do that on production boxes, I swear. Let's just make sure that there's no other controllers running. No, that's fine. I want to make sure that the Mininet environment is nice and clean as well. I'll do that in the bottom window because it's a Mininet thingy. Yep, running in one virtual machine. So there's running in VirtualBox. So it's free. It's just running in one virtual machine. Those are 2 SSH windows into the same machine. All right. So what I want to do now is I want to start the controller. Now the controller we're using is called Aru, which is Japanese for dragon and flow, I believe. Tomohiro will correct me if I'm wrong there. And what we want to do is we want to start it and pass it an application, because it's absolutely no fun to have the controller decide what the network's like. We want to decide what the network does. And so the application I'm going to pass it is one called Simple Switch. So there we go, I'm typing that in, and there's my controller started. The controller is a Python framework, so those of you that know Python will be seeing some familiar stuff up there. So that's the control plane there, just sitting there waiting, okay? And what my Simple Switch program does is effectively just implement this logic here. It creates a table to map MAC addresses to ports. That's all a switch does. Every time a packet comes into the switch, it parses the packet, stores it in the mapping of source MAC to input port, looks up the destination MAC. If it finds the next hop, it creates a flow rule so that next time the packet comes in, It doesn't even come to the controller. And then and if it can't find it, it floods it to all the ports. So here's the command, here's the mininet command down here, which starts up a simulation environment which looks exactly like the ASCII art that I had before. So if I start that, what we're going to see is in the bottom window, the environment will start, it'll start one switch and 3 hosts. And in the top, we'll see the Openflow switch connect to the controller, check in and say, hi, I'm here. Do you want to give me some flows? There we go. So what we saw here, adding hosts, 3 hosts, 1 switch, connecting to the controller. What we saw here was the switch connecting in. Oh, this has got a laser. Warning, don't, ooh. Yeah, cool. So here's the switch here connecting in, telling me about its features, what version of Openflow it's running, all that sort of stuff. And then here I'm seeing that I'm getting events. So the Openflow protocol is event-driven, really. So, the data plane tells me about things that are happening. It says, packet in. I got a packet. I didn't know what to do with it, so I'm giving it to you. So what happened here was I got an Openflow packet in, and then my little Python script, that simple switch app, said, oh, I'm going to parse that packet, and it's actually coming in from MAC address 3 on port 3, and it's destined to MAC address 3333. Anyone recognize that? There you go. Have another virtual chocolate fish. Man, watch those virtual calories, yeah. And then, so I can associate that incoming MAC address with a port, and that's that mapping, right? Cool. Now, remember I'm doing all this talking about flows, all right? These create these flows, these flows. Well, one of the good things I can do with Mininet is I can actually dump the flows. So this shows me all of the current flows that are on the switch. And the interesting one is the one right down the bottom here. I realize this is a bit small, bear with me. It has some cruft at the front, some stats, and then priority equals 0, actions equals flood, and controller :64. Now what that tells me is it's a priority 0 flow, so it's the lowest priority, so it gets run if nothing else matches. But also it has no match conditions, so it's going to match every packet that makes it through to that flow. And I'm going to flood the packet to all the ports, and I'm going to copy the first 64 bytes to the controller. So that's all that flow does. But that's how those packets got to my controller that we saw before. Because all of these top flows weren't there. And the only flow that was in the switch was this bottom one. So when the packets started coming in, I started flooding them up to the controller, and the controller parsed them, decided what it wanted to do with them, and then it made these other flows. And if we have a look at some of these, we can see here are some match conditions. If a packet comes in port 1 with a data link source of MAC 1 and a destination of all Fs, which is a Ethernet broadcast, yep, then flood it to all ports. So automatically I've got a flow rule here now to handle Ethernet broadcasts from that one MAC address on that port. So broadcasts will never go to my controller anymore. And there's one of those for the other one, and then there's some that take LLDP and drop it, and these ones are V6 neighbor discovery, I think. So I'm building these flow rules based on seeing packets on the controller. So I want to show you guys a little bit more. No. Yep. The flood meant that they were flooded as well as passed up. If I took that flood out, the first 64 would be just passed up, and then the rest of it disappears into the big bit bucket. Okay? So no buffering happening. Yes, true. Yeah. So that all that's happened here is that I've got some multicast up here, and I added some rules. What if I want to ping between two of the hosts? So I go H1 ping H2. Here we go. So that ping's happening there now. That's working fine. But let's look at what happened up on the controller. So I had a packet in, and it was from MAC 1 to MAC 2, and I added a unicast flow. And then I did that, I saw that twice, once for each direction, and then I didn't see any more packets on the controller. So what do you think happened? Exactly. So I only saw the packet arrive at the controller while the control plane, while the data plane had no idea what to do with it. It didn't match any flow rules. And the minute I added a unicast flow down on the data plane, the packets stopped going to the controller because they stopped matching that priority 0 rule, but the packets are still flowing. So we can actually see that by dumping the flow rules out again. And there's a couple of new rules there. This one here's new. Priority 100, so the highest priority that I've got in the table. And if the data link sources MAC 1 and data link destination is this, actions, output, port 2. So I'm doing a match on source and destination MAC and source port and putting it out just that port. Okay? And I can see that it's matched 63 packets, which is kind of similar to the number of pings I've done, and there's the one in the opposite direction. So this is what's meant by software-defined networking. I'm doing my networking. I'm doing real hardware, hardware speed data plane networking, but it's being controlled by a little Python script. Okay? I'm not saying go out and deploy global networks on a Python script, but I think you guys get the point. So I can scale this up. I can stop miniing it and give myself, so if I stop that, dunk, it dies. And I can then give myself one switch and 10 hosts. There we go. And then there's a cool command called ping all, which just does a ping matrix, every host to every other host. So what I reckon is going to happen here when I do this is a massive amount of packets are going to make it up to the controller because the data plane has no idea what to do with them. A lot of unicast flows are going to get created, passed down to the data plane, and when I run the command a second time, I reckon everything's quiet. There we go. So there's the ping output, sweet as, we didn't drop any. There's all the unicast flows being added. And now I can run that to my heart's content, and nothing else is making it up to the control plane. Everything's being hardware switched. And I can confirm that by dumping the flows again. There we go, there's a lot more flows this time. Here we go. Some of them output port 9, output port 10, output port 7, and they've all got 29 and 30 packets against them. Okay? I can even do an iperf. For those of you that know iperf, this is like just how quick can I get packets from A to B, right? Turns out 1.43 gigabits a second across my VM. Okay, but none of them made it up to the controller. So, oh yeah, we're 5 minutes late. I'm calm.
so that's an example of how I can get software to control a data plane. As I say, I will put up that VM and you guys can start playing with this, play with the Python a bit. What I make the students do is I make them do things like either implement spanning tree, implement it at a network-wide controller level. I hate that idea because if you have control over your entire data plane, you don't need loop detection and prevention, just don't install loops. Don't install flows that have loops. But I make them do it anyway. The other cool thing that I make them do is automatic network topology detection. You can generate LLDP packets and get the data plane to put them out for links, and then have flow rules that say whenever you hear an LLDP packet, put it up to the controller. So you create these packets and flood them, and then they cross some links that you have no idea where they go. When they get to the other side of that link, all the data path elements, pass them back to the controller. And then you can graph your network. So that's an actual mini-net network, which I ran the code on to do automatic topology discovery, put all of the nodes and links into a graphing, add node, add link, blah, 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 and there you go. You might think that's kind of, wow, pretty tree. That's the REANZ network in New Zealand. That's mocking that up on Mininet and saying, I wonder what it looks like. Go and find me whatever the network looks like. Now, in the negative 5 minutes I have left, I reckon it would be awesome if your network mailed you and told you, hey, I've noticed that all of the flows through your network and all the stuff in your network, things would go a whole lot better. I'd be able to do more if you went to this data center and joined a connection between port 5 on this and port 6 on that. And you can get that sort of functionality here because it's just compute. It's just software. And in the world we're in today, Moore's law and all that this morning, software and algorithms is cheap. If you want something to run, if you want software to run faster, you buy more cloud, right? You buy more virtual cycles. So as long as your hardware can forward the packets as quickly as you want, doing complex stuff about how those packets get traversed is just a software problem, and we kind of already know how to solve those. So thank you. I won't take up any more of your time. I hope that was interesting. I will get the VM up and I'll post it out to the APNIC talk list or something. Thank you very much.